So this is the tutorial session for lecture 2 about convergence of theories. We have introduced several criteria to help you to determine whether a theory is convergent or not. And we will consider the exercise questions here. We go through all the techniques in the lecture 2. So the first question is about positive theories. So every term is positive. Okay? So the question is whether this theory is absolutely convergent or not, or conditionally convergent. First, this is positive theory. For positive theories, convergent is equivalent to absolutely convergent, right? Absolutely convergent is simply considering the absolute value of this series. Okay, you consider absolute value of the series. But this is positive theory, so absolute value of every term is itself. So for positive theories, the simplest method is ratio test. By ratio test, we mean that we need to consider the ratio between next term and the current term, and then take limit. For this question, if you consider next term over current term, you would get an n plus 1 in the upper side because you have a factorial of n plus 1, which divided by n factorial is n plus 1. So, and this is 100 to the power n plus 1 divided 100 to the power n, so you get 100. Anyway, when n tend to infinity, you would get infinity. Right? Because n tend to infinity, in the upper side, you get infinity. So when the limit of this ratio is bigger than 1, infinity is clearly bigger than 1, right? Then the series is divergent. This is the ratio test. This is another series. This is not a positive series because sine function may be negative, right? So sine n may be negative for some n. This is not a positive series, but we can consider the absolute value. If you take absolute value of every term and then use comparison test, sine function is always smaller than 1, right? The absolute value. So this is always smaller than 1 over n squared. While the bigger series, you know it is convergent. There is an example in the lecture note that this series is convergent. So the smaller series must also be convergent. And since the absolute value series is convergent, the original series is called absolutely convergent. Right? So we have used the absolute value convergent, and we also use the comparison test. We removed the sine function because it's smaller than 1. Okay. This is a similar question, but it's written in a different way. So when you meet such questions where power n exists in some base number, so we have base number to some power n, base number to some power multiple of n. So when you meet such questions, you should use the ratio test. Okay, when you meet n squared such questions, so n is the base number instead of power, you need to use integral test or comparison test. Remember this, because when you have n to some power, n is the base number, so ratio test would not give you a good result. If you consider ratio test, you get a limit of the ratio to be 1. Okay, when the limit of the ratio is 1, you cannot conclude anything. So in this case, you should use comparison test or integral test or other test. Well, when n exists in the power, the base number is constant. In this case, you should use ratio test. A ratio test would give you this. Let's look at this. So you get a 10 here, while you get 4 squared from here. So you get 10 and over 4 square. Well, when n tend to infinity, this term tend to 0, so it can be neglected. In the end, you get 10 over 16, which is smaller than 1. When you get a number smaller than 1, the series is convergent. Okay. I hope that you have considered this question by yourself. Now, please consider this question by yourself. I'll give you 1 minute or 2 minutes. You consider this first by yourself. Don't look at the answer. Just try to find out whether you can find the correct answer by yourself. Is this series convergent or not? You consider this by yourself. Okay. So this is a general series first. It's not a positive series because you have -1 here. For general series, you should try 2 methods. First, you consider absolute value of the series to see whether it is convergent or not. Okay. If you consider absolute value of the series, you can remove this -1. And you can use ratio test. You will see that ratio between next and current term will be 1.1 over 1 plus something, 1 over n here to some power. But when n tend to infinity, you would get a number, 1.1, right? Which is bigger than 1. Although it's very small, it's still bigger than 1. Okay? Even if 1.1 is a very small number. If the limit is bigger than 1, you should draw a conclusion that this absolute value series is not convergent. Okay? It's not convergent for the absolute value series. But how about the original series? So the absolute value series is not convergent. The original series can still be convergent. It's possible, right? But for this question, it's not convergent. The reason is that if the ratio of the limit is bigger than 1, then you can conclude that the next term is always bigger than current term in absolute value. So if next term is bigger than current term, for n is sufficiently large, then this an will not decrease to 0. It does not tend to 0 because next term it becomes bigger. If it does not tend to 0, it violates the necessary condition. For series to be convergent, a necessary condition is that an should tend to 0. But it does not tend to 0 because next term always becomes bigger, right? So therefore, this necessary condition is violated. Therefore, the original series is not convergent. So the necessary condition is for general series. It's not only for positive series. This condition is for general series. For series to be convergent, this condition is necessary, right? If this condition is not satisfied, you can immediately draw a conclusion that the series is divergent. Okay. And how about this series? Well, this is the sign is alternating because you have -1 to power n. And if you look at this, the denominator, it's an increasing function of n in the denominator. Therefore, when n becomes bigger, log n plus 1 becomes bigger. And then log n plus 1 becomes bigger means that 1 over log n plus 1 becomes smaller, right? This is a decreasing function. This is decreasing function of n. Therefore, you have a alternating series. It's typical not alternating series, which is convergent. So this series is convergent. The question is whether it is absolutely convergent or conditionally convergent. Okay, so it is convergent. But if you consider the absolute value series, remove the negative sign, this is divergent. Okay. So why this is divergent? Because you can use integral test. For positive series, well, this is a decreasing function of n. You can compute the integral of this, and the integral would be infinity. Integral test shows that the series is divergent. So for the absolute value series, it is divergent, but the original series is convergent. In this case, it is called conditionally convergent. Right? This is definition of what is conditionally convergent. So it's not absolutely convergent, but it is convergent. Okay. And how about this term? Is this convergent series? First, this is a positive series. There's no negative sign here. It's positive series. Then for positive series, you only need to know whether it is convergent. Okay. Give you 1 minute to consider this question. So you really need to spend some time to work by yourself. Okay. You should not only listening to me. You should work by yourself. Try, and then when you meet some difficulties, and then you know where is the difficulty. Then when I give you the answer, you should know how the difficulty can be overcome. You should first try yourself. Give you 1 minute. Yeah, I will upload the video to the Blackboard. So I will also upload the PDF. Okay. So in addition to the video, I will also upload to the PDF. So let's look at this question. First, we know this is a positive series. And I wouldn't use ratio test for this question, but of course you can try. You can try to use that. But because this question looks so simple that we have a big number to power n in the denominator. If you have a big number to power n, then although this number is not fixed, you should know that it is a big number, right? When n is big, this is big. So let's say it would be bigger than 2 when n is large. So this series would be smaller than n over 2 to the power n. Okay. And for this bigger series, you can use ratio test, and this becomes easier, okay? Because it's a fixed constant. If you use ratio test, you would get for the bigger series, you would get this. And when you take limit, you will get half, so which is smaller than 1, right? So for the bigger series, it's easier to use the ratio test, and you know that it is convergent. Therefore, for the smaller series, it must also be convergent, right? This is comparison test. So in this question, you use the both ratio test for the bigger series and comparison test. You get the smaller series is also convergent. Okay. If you use directly ratio test for the original series, the computation is a little more complicated because you don't have a fixed number 2 here. If you use the ratio test directly, what you get is log n plus 1 to power n plus 1 over log n to power n. So the expression of this is not pretty. Okay, it's ugly. So if you want to simplify your calculation, you can first use the comparison test. Okay. Now, how about this? If you consider this, first, what is this term? This is roughly 1 plus something. 1 plus something is not small, right? If this is not small, it does not tend to 0. If it does not tend to 0, then the series is not convergent. This is the necessary condition. Okay? So if you take limit, actually this tends to e. It's not 0, so it violates necessary condition. Therefore, the series is divergent. And how about this? I give you 1 minute to consider this question. This is different. So here you get an additional log here. If you have a log here, you should know that log 1 is 0, right? So when n tends to infinity, this becomes 1, while log 1 becomes 0. So this term indeed tends to 0. So the necessary condition is satisfied. In this case, you should use other method to determine whether the series is convergent or not. I'll give you 1 minute. First, you try this question by yourself. So this is alternating series, right? So why? Of course, the sign is alternating. You have negative 1 to power n. The sign is alternating. The question is whether this is decreasing function. So you should examine here. When n increase, 1 over n decrease, right? When 1 over n decrease, log 1 over n plus 1 decrease. So really, this is a decreasing function in n. So it's so the series is convergent. As an alternating series, it is convergent. The question is whether it is absolutely convergent. Okay? So if you don't take absolute value, its alternating series, it must be convergent. While if you consider absolute value, it becomes different. Because if you remove the negative sign, you get this series. But this series is not convergent. Okay? The reason is that log 1 plus 1 over n is roughly equivalent to log, so this is roughly order 1 over n. So this is roughly 1 over n. Well, you know that 1 over n, this series is divergent because you can use integral test. Integral of this function would be infinity, right? If you consider integral of 1 over x, give you infinity. So 1 over n, this series is divergent. Therefore, this series is also divergent. Okay. Of course, you can use other techniques. You can split it into 2, right? And then sum up this. The sum of the first n terms would be log n plus 1. And then you let capital N tend to infinity, you would get infinity. But this approach not always work. Right? It does not always work. The reason is that what if you have 2 plus? What if you have 2 over n here? Then it will become different. Okay. In this case, you could not get cancellation. You cannot get cancellation. Okay. But the first method is easier. Still, this is order 2 over n. If this is order 2 over n, then 2 over n, the series of 2 over n is divergent by using integral test, right? So this is another method to consider this question. Well, you know that log 1 plus x is roughly order x as x tend to 0, right? So they are equivalent because you can use L'Hopital's rule to consider the limit x tend to 0. If you consider the limit when x tend to 0, if you use L'Hopital's rule, the upper side, by taking derivative of log function, you get 1 over 1 plus x. By taking derivative of denominator, you get 1. So the limit is 1. This explains that log 1 plus x is equivalent to x when x tending to 0. So they are roughly the same the same amount. So therefore, for this series, this is roughly order 2 over n. While you know that this series is divergent. Okay. Let's consider this more complicated question. while you have this something to power n, but this is not a number. This is also a complicated expression of n. But if you just look at this base number and think about this, think about the question, how large is this term? Okay, then you can see that when n tends to infinity, this is roughly 1/2 because this is 1 times n squared divided by 2 times n squared, right? So the limit of this would be 1/2. So how do you get the limit? For all such questions, you can divide the biggest term, n squared, in both upper and lower side. If you divide n squared, you get this. Then when n tends to infinity, this tends to 1/2. 1 plus 0 over 2 plus 0, right? So when n is sufficiently large, this is roughly 1/2. If this is roughly 1/2, you get 1/2 to some power n, right? You get 1/2 to some power n. This is geometric series. Series would be convergent, right? But this a more rigorous argument is that since the limit is 1/2, therefore when n is sufficiently large, this is sufficiently close to 1/2. If this is sufficiently close to 1/2, then it would be smaller than any number bigger than 1/2, such as 3/4. So 3/4 is bigger than 1/2, right? So when n is sufficiently large, this is sufficiently close to 1/2, therefore it's smaller than 3/4. And therefore, it's smaller, the series, every term will be smaller than 3/4 to power n when n is large. While the latter series, the bigger series, is convergent. It's geometric series. Therefore, the original series is convergent. So this is comparison test. If you use ratio test, you need to compute a very complicated expression. So that's more complicated. But if you use such comparison test, it's very concise. Okay. So I give you a half minute to just look at this question, think about it. Okay, so here the expression of an is not explicitly given. You are given a relation between next term and the current term, but by using this relation, it's difficult to find the expression of an. But we really don't need the expression of an, right? We only need to know this is a positive series, because next term is always equal to current term times positive number. So every term will be positive. This is a positive series, therefore you can use the ratio test. Well, this relation tells you the ratio, right? The ratio would be this. If you take limits, the ratio has a limit bigger than 1, therefore the series is divergent according to ratio test. So sometimes we don't need the expression of an, but from the relation, between next and current term, we can also determine whether the series is convergent. Okay, first you need to know that this is a positive series because next term is always equal to current term times positive number. The series must be positive. Now this is another question that the expression of AN is not given, but a relation between AN plus 1 and AN is given. Then you consider whether this series is convergent. Okay, so here, if you look at this number, the ratio, right? If you use ratio test, first it's also positive series because this number, the ratio is always positive. Okay, cosine n is smaller than 1, bigger than -1. So 2 plus cosine n would be positive number. Since the ratio is positive, you get a positive series. And if you look at this ratio, by taking limit, you get 0, right? So because the upper side is smaller than 3, but the lower side tends to infinity, it would be smaller than 3 over infinity, right? The limit would be 0, smaller than 1, and therefore the series would be convergent. Okay, so this is typical question of a ratio test, that you can compute the limit of this ratio. While sometimes you would meet more complicated questions. I will give you 1 minute to consider this. So if you change the square root of n to a constant number, then if you consider the ratio, the limit doesn't exist. In this case, can you still draw some conclusion? Give you 1 minute to consider this. Okay, so if you directly use ratio test, you consider the ratio between next and current term. Well, this would not work because the limit doesn't exist. Okay, the limit doesn't exist. But limit doesn't exist doesn't mean ratio test doesn't work because you still see that this is a number smaller than 1, right? So you could use this argument. You use a comparison test. So this is always smaller than a 3 in the upper side. So it's always smaller than 3 over 4. Okay. Therefore, you can iterate this. Next term is always smaller than 3 over 4 times current term, then smaller than another 3 over 4 times its previous term. You can iterate this inequality. You would see that an would always be smaller than 3 over 4 to power n. So, well, this on the right side, you get a geometric series which is convergent. And therefore, the smaller series must also be convergent. So this is basically comparison test. Okay. ratio test cannot work directly. But the ratio is smaller than 1, you know that. So you can iterate this. Well, the last topic in lecture 2 is about a series of functions to determine for which value of x the series is convergent. Okay. So the solution is written down here, but I would ask you to try to consider this question by yourself, how to get the answer here. I'll give you half a minute on this question. Just consider how do you determine for which x this series is convergent. Okay, so you can regard x to be a fixed number and determine whether this series is convergent. This is the method. So let's say x is just a fixed number, and then this would be a geometric series. And we want to determine whether this geometric series is convergent, right? And we would require the absolute value of the base number to be smaller than 1. So in this case, the series would be convergent. If the base number is smaller than 1 in its absolute value, then it's convergent. Otherwise, it's divergent. And this would give us the result that absolute value of x should be smaller than 2. X should be from -2 to +2. So this is the standard argument. You should first regard x to be a fixed number, any number, and you determine whether the series is convergent. Okay, you find the condition. And from the condition, you would furthermore write down the range of x, satisfying this inequality. Okay, so this is a more complicated question. So for which x this series is convergent? First, as I mentioned before, that this is roughly order x over n, right? I have explained this before. So in this question, you should first know that this is roughly this series. Well, for the right-hand series, it's easier to consider whether it is convergent. So the method to derive this equivalence condition is this. You consider the limit when y tend to 0 by using L'Hopital's rule. You will find the limit is 1. So this means that log 1 plus something is equal to something, roughly. Okay, so this ratio is roughly 1. So, which means that this log 1 plus x over n is roughly x over n. So it would be bigger than half times this number, because it's roughly equal to 1. Roughly equal to 1 means that it's bigger than half. So while the right-hand side series is divergent, except when x equals 0. Right? If x equals 0, of course, every term is 0, it would be convergent. Otherwise, for non-zero x, the series is divergent. So therefore, this series is divergent for non-zero x and convergent for x equals 0. So the answer would be divergent when x is not equal to 0, convergent when x equals 0. Okay. When x equals 0, every term would be 0, so the series would be convergent. Okay. If you add -1 to some power, this becomes alternating series. If this becomes alternating series, for example, when x is positive, this is a positive number, and decreasing in n, so it's a standard alternating series. Well, when x is negative, this is also alternating series. Okay, but this would be roughly equal to negative x over n. So therefore, generally speaking, for all x such that this function makes sense, the series will be convergent. Okay, but you still need to require x to be bigger than -1. The reason is that n starts from 1. For the first term, this would be 1 here. This becomes 1 plus x. So the domain of the logarithmic function should be a positive number inside the bracket. So x plus 1 should be positive, at least when n equals 1. Okay. When n equals 1, you get 1 plus x. It should be positive. This requires x to be bigger than -1. So otherwise, if x is smaller than -1, so when n equals 1, this term doesn't make sense. Okay. Well, 16th question, it's also alternating series for some x. You should write this into more clearly for this is -1 to power n. This means that sign is alternating. But the second part should be written as this to power n. Okay. You get this number to power n. Let's see. This is smaller than 1. The series is convergent because it's smaller than the geometric series. Right? The reason is that when this is a space number is smaller than 1, you get a geometric series. Well, this part would always be smaller than 1. So you use comparison test in this case. Using comparison test, this smaller than 1, this smaller than geometric series. Okay, in this case. Well, what if this is bigger than 1? the series would be divergent because you get a base number bigger than 1. Okay, when the base number is bigger than 1, the term becomes bigger and bigger. When n increase, this term becomes bigger. So it does not tend to 0. So it's divergent. But what if this number is equal to 1? In this case, you get an alternating series. When the base number is equal to 1, you simply get this alternating series. This alternating series is convergent. Okay, so to conclude, in the first case and the third case, the series is convergent. In the first case, x should be smaller than log 2, right? And in the third case, x is equal to log 2. In these cases, the series is convergent. So x should be smaller or equal to log 2, okay, in the end. So for x in this range, the series is convergent. So that's all for today. Hope that you can follow me. Otherwise, you can ask questions or send me emails.